shall continue further. Now I'll present to you the introduction for our topic. The topic for this video is 2D flow in a pipe. We use CFD simulation to simulate the action of fluid in a pipe. Before getting to know the 2D flow in a pipe, we first needed to know what is 2D flow and why we need to learn the 2D flow. 2 or 3-dimensional flow refers to the number of spaces coordinated required to describe a flow. It appears that any physical flow is generally 3-dimensional, but these are difficult to calculate. We need to simplify the flow by ignoring the changes in the directions of the flow. By doing this, we can reduce a 3-dimensional flow to a 2-dimensional or a 1-dimensional flow. Then, what about 2D flow? 2-dimensional flow is a type of fluid motion when the flow velocity at every point is parallel to a fixed plane. The velocity at any point on a given normal to that fixed plane should be constant. Mathematically, for 2-dimensional flow, written at the slide, fluid flow in pipes can be affected by many different factors like the viscosity, density, and velocity of the fluid. Studying the flow in the pipes in 2D can help us to study those factors easily and help to solve the pipe flow problem we face during our daily life.
Hi everyone, my name is Jovan and I will be the one that introduces the theory related to our topic. So that you guys can easier to understand the theory of 2-dimensional flow in pipes, I will start by explaining what is going on when the fluid is flowing through the pipe. So, when the fluid is flowing through the pipe, the fluid will contact the pipe wall. The pipe wall has surface roughness and the amount of roughness will affect the fluid drag. The drag between the layers will spread them apart and each layer will move at displacement. This drag rate decreases as the distance from the wall increases. So, it means that the velocity of the fluid at the wall will be 0 and fastest at the center. This means the center core of the fluid will always exit first. Because of friction caused by the pipe wall, the fluid moves slower near the wall. This slow-moving fluid is known as the laminar sublayer. In this layer, the fluid will slide over itself. The thickness of the sublayer can vary from 10 of a millimeters to several millimeters, depending on the speed of the flow, the height of the wall projection, and the fluid physical property. The sublayer only develops in turbulent flow. At slow flow, the sublayer blend in with the pipe laminar flow. As we said just now, at low speed, the flow across a pipe is laminar, and the fluid will slide over itself. As the speed becomes faster, the transition from laminar to turbulent flow will develop. The laminar sublayer is always present against the pipe wall, but as the velocity rises, the energetic stirring at this became to impact more deeply and the sublayer began to thin. At still higher velocities, the sublayer thins further and the taller roughness peak stick into the turbulent region. Where the sublayer covers the roughness projection, the wall is considered smooth. When the wall roughness pops out of the sublayer, the wall is considered rough. This means the same wall can be both smooth and rough depending on the fluid velocity.
Okay, the objective for 2D flow in pipe, our main objective is to find the velocity variation in the pipe by using the CFD simulation. Next, to learn how to set up the CFD simulation. And last but not least, we need to learn how to achieve a high level of credibility and confidence in the result from the CFD performed. Okay, next for geometry detail and the dimensions. From our group, we can see that at figure 2.0 dimension of pipe, in the simulations, we will create a 2D pipe with a 20mm diameter and 100mm length. And we will considering an internal laminar flow in the pipe, and the water flows in the pipe with a velocity of 0.0005 meter per second.
Hello everyone, I'm Janagan and I'll be doing the simulation process. At first, we'll look at the dimensions of the pipe. The diameter is 20 mm and the length is 100 mm. The water flows in the pipe with a velocity of 0.5 mm per second. We will be considering an internal laminar flow in the pipe. In the ANSYS Workbench software, click and drag the fluent analysis system to the project schematic window. Now click the geometry and under the properties list, change the analysis type from 3D to 2D since we are doing 2D analysis. And now right click the geometry and click the new design modeler to design our geometry. In the design modeler, make sure the units are in millimeters and then click on XY plane as we are going to draw on it and click on Z arrow to make the plane normal to the screen. And now use the sketching toolbox to draw the rectangle on the plane. Now in order to specify the dimension of the rectangle, we'll be using general dimension tool. Right now click on this line as the width and on this line as the length. Right now write the value of the length as 100 mm and the value of the width as 10 mm. And now we're going to create a surface from this sketch. For that, click on concept, then click on surfaces from sketches. Now click on the sketch and apply it as the base objects. Right now, right click the surface and click generate. And make sure the surface body is selected as a fluid surface since the meshing of fluid domain and solid domain is different from each other. Now click generate and now we can exit this design modeler software. Right click the mesh and click on edit. Now we can see the geometry that we have created previously. Now we're going to generate the mesh by right clicking the mesh and click generate mesh. Now the mesh is created using the default element size. We are going to reduce the element size to 1 mm. And generate the mesh again. In order to check the quality of this mesh, we are going to change the display style to aspect ratio. Now we can observe that the mesh cell is not distributed properly. Therefore, we are going to use adaptive sizing. And generate the mesh again. Now the mesh cell is distributed uniformly. Click on the edge selection tool to name all the boundaries. Click on the bottom edge, right click and click on create name selection. Name this edge as axis and click on OK. And for this top edge, we're going to name it as pipe wall. And for this boundary, we're going to name it as inlet. And for this, we're going to name it as outlet. Now these are all the boundaries that we have named. Now right click on the mesh and click on update. Bottom here we can see the mesh translation to the fluent has been successful. Right now we can exit the meshing process. Right click the setup, then click on edit. In the Fluent Launcher, choose the double precision option, then click on Start. Now in the CFD solver, we're going to choose the 2D space as axis symmetric. Then click on Check. Now click on Report Quality. In the report, we can see the value of the maximum aspect ratio. Then we're going to choose the model. Double click the viscous and then choose lamina. Then click on OK. Now we are going to choose the material. Click on Fluid and then find for water liquid. Then click on Fluent Database. There we go, water liquid. Copy that and close it and change, and we can close it. Right now click on sal zone condition and we are going to assign the material to the surface body. Click on edit, choose water liquid, apply that and we can close it. The operating condition must be in atmospheric pressure. Now we're going to click on boundary condition, and the type of the boundary condition has been automatically selected. Now we only have to input the value of the velocity magnitude in the inlet. It will be 0.5 millimeter per second. Apply that and close it. Click on Methods, choose Simple Scheme, and now click on Monitors and select Residuals. Reduce all the residual values to 10 to power of -6. Click OK. Click on Initialization and select Standard Initialization and compute from inlet. Click Initialize. And now click on Run Calculation and set the number of iteration 1000. Click Calculate. Here you can see the calculation is completed when the solution is converged. Click on Graphics and select Contours. And now let's select contours of velocity. Click on Display. Now we can observe the contours of velocity magnitude. And similarly for the contours of the static pressure, click on Pressure and click Display. Now we can see it. And now click on plots, then select XY plots. For y-axis, choose velocity and select axis and click on plot. Here we can see the velocity variation along the central axis. That's all from me. Thank you.
Hi, it's me again. So for the results, there are 3 results we can get from this CFD simulation. The first one will be the velocity magnitude. Our result is present in the form of contour. According to this contour, it can be seen that the fluid flow velocity at the pipe central axis is maximum and decrease toward the pipe wall. The next result will be the static pressure. As we can see, the fluid will have higher pressure at the inlet part of the pipe and it will start to decrease toward the outlet part of the pipe. Here, we will plot out the velocity plot diagram which show the velocity magnitude along the pipe axis. According to this velocity plot diagram, you can see that the velocity increases when the position of the fluid in the pipe moves further.
For a relationship between result and theory, I will start with the velocity magnitude. According to the theory, a fluid flowing through a pipe will contact the pipe wall, and the pipe wall has a surface roughness that can affect the drag on the fluid. The drag between layers shears them apart and each layer moves at a different speed. The shear rate decreases as the distance from the wall increases. Therefore, the velocity at the center region will be the fastest. Our contours for velocity magnitude diagram show that the fluid flow velocity at the pipe central axis is maximum and decreases towards the pipe wall. That means our result is successfully related to the theory.
Next, pressure. Pressure also can be related between our result and theory. According to our result, the fluid has higher pressure at the inlet part of the pipe and it will start to decrease towards the outlet of the pipe. Laminar flow is characterized by the gliding of concentric cylindrical layers past one another in orderly fashion. The velocity of the fluid is at its maximum at the pipe axis and decrease sharply to 0 at the wall. The pressure drop caused by friction of laminar flows does not depend on the roughness of the pipe. Last but not least, the stimulation has proven the pressure loss along a pipe with laminar flow is proportional to the velocity.